Okay, so welcome back to the second in our series of public talks. This talk is going to be given by Avyarthana Ghosh. Well, so thankfully I don't need a piece of paper to introduce Avyarthana. Avyarthana is the very first batch of PhD students of the Center of Excellence in Space Sciences India, which initiated in 2013. There were three in those batch of students, Avyarthana, Prantika and Rakesh, if I recall correctly. Avyarthana obtained her bachelor's degree in physics from Lady Brahman College. Then she did a MTech from the Institute of Radio Physics and Electronics at Calcutta University, following which she joined here for a PhD program. The CESI is a unique center in the sense that it's a multi-institutional center involving various institutions from around the country. One parallel of this is the JAP program, the Joint Astronomy Program at the Indian Institute of Science, where one can in principle do the coursework at IISc, but then go to any of the participating institutions for their research. So IUCA was one of the institutions which is part of CESI. So Avyarthana did her coursework here in ISRO Kolkata and then joined IUCA, moved there to work on a project that was conceived together with ISRO Kolkata, IUCA, INESRO Astrophysics and some other organizations, namely the Solar Ultraviolet Imaging Telescope on board the Aditya L1 mission. So Avyarthana is a PhD student who contributed directly to the planning as well as the development of an instrument that is about to fly in space next year on board the Aditya L1 mission. We started off from very humble beginnings in the Horingata farm on the other side of the campus. We've shared some lovely time together. You have been blessed with this rather nice campus now, but the beginnings of both CESI and ISRO Kolkata were in a much more rundown place, which is still a very nostalgic place for us because we did some really good science and had some good times. We have NB, who was also there right next door in the, we used to call that the Mathematical and Theoretical Sciences, MTS building, which is now full of creepy crawlers, like plants which have gone inside the building if you go there. We started off from there, but I think Avyarthana is an example of what one can achieve if you are in the right place, in the right time, have the right opportunities, and can work hard to get to where you are today. Today, she is at TCS Research, where she is helping them set up an analysis group for space-based Earth observations for various domains of services which are useful for the society. So with that, I'll welcome Avyarthana on the stage to talk about an ISRO student's journey to build a space instrument for India's mission to the sun. Avyarthana.
Thank you very much. So yes, I had a very humble beginning here with two of my batchmates and with Dibyendu and NB sir and other people. And from there, we went to a position where I could take part in building and testing of some of the instruments which I'll be talking about today. And this mission, of course, is Aditya L1 mission, and the instrument that I have been talking about is, which Dibyendu also told about, is the Solar Ultraviolet Imaging Telescope. So I would get going. Okay. So the brief introduction Dibyendu has already given. So I started off, I did my schooling from South Point High School, followed by a BSc from Lady Brahman, and from University of Calcutta I did my further studies. Then I joined CESI here for my grad school, and then was deputed to IUCA for developing the instrument, the Solar Ultraviolet Imaging Telescope. After finishing my PhD, I actually joined IUCA formally, along with being deputation at ISRO for my postdoctoral position. I continued there for 2 years, and last year I have moved on to join TCS Research as their scientist. So why am I here? I am here to share with you my experiences of working for the Solar Ultraviolet Imaging Telescope, Like from teenage, when we start hearing about spacecrafts and space missions, we all think about fancy stuff and we think that, okay, one day we will also be doing that. So I have been blessed with the opportunity of doing a part of it at least, and this is what my contribution has been. So my PhD thesis actually had two parts. One was an observational study, multi-wavelength or solar observational studies of solar atmosphere. That was very critical for development of suit, because with that we could understand what all science has already been achieved by the space missions of NASA, JAXA, ESA. Because remember, Aditya L1 mission is the first solar mission, space-based solar mission that India is sending. So this has to be doing some cutting edge science. So that is why we needed to have a background of what all is already done. And that is where these observational studies came into use. And once we did those studies, we could put down all the scientific objectives of suit in a clearer way, and then the technical requirements for achieving those objectives. Once we had those technical requirements, I moved on to designing end-to-end performance modeling, stray light analysis, since it's an imaging telescope as the name suggests. Stray light, so stray light is going to kill an instrument if we have unwanted light in an imaging system. I was part of the alignment, integration, space qualification and calibration of various optical components. This is a very intelligent system. Just as Varun was saying, it is completely automated. It is mostly automated because all onboard, like all decisions that the instrument has to take for its observations are mostly taken on board. Few of them need ground intervention from the ground station, but most of it is designed to be done or in an automated way online on board. So I was working on that also, and also I was planning out joint observations with other existing and upcoming space missions for solar observations. In addition to that, my contribution has been to the study of failure modes and effects analysis for this instrument. So every component, including a nut or a bolt, what is the criticality of that particular nut and bolt of that particular component in the entire instrument, how severe the failure of that could be. Everything was done, and a huge document was made pointing out every single thing, including a tape. If a tape falls off, then falls off. If a covering falls off, if an insulating layer falls off, what is going to be the effect on it? How worse the instrument is going to suffer. So we are all aware of stars, but actual star is the sun. And this entire thing began with NASA's mission, Living with a Star. So we know that Varun was talking about sun being a humble star. Yes, it is true. The sun is a humble star which has its origin from a remnant supernova, and the mass is about 10 to the power 30 kilos, and the radius is about 696,000 kilometers. It's a middle-aged star, so it is going to live for another about 4.5 billion years, until before it turns into a red giant engulfing the Earth, going up to maybe spreading up to Jupiter, and then collapsing into a white dwarf. But this is not like, we don't see anything interesting like finding gold and everything. So we see the sun as a blank yellow disk in the sky. So what is important about it? So when you actually observe the sun with a naked eyes, you can see this kind of a yellow disk. And when you use some very high powerful telescope from ground, you are going to see sometimes there are these dark spots on the sun which are known as sunspots. And these are, some people actually know that these are regions which have stronger magnetic field with a more complex model, more dynamically more evolving, faster, dynamically more happening. But the main thing comes when there is an eclipse. So it is only during the eclipse when the disk of the sun, that yellow disk that you see in the sky, that is blocked off, only then you can see the atmosphere of the sun. And the atmosphere of the sun has a variety of structures to offer to see. So these are these loop-like structures, these arcades, helmets, streamers, everything are there. You will see tiny eruptions there at the edges. So the only way you can see this kind of solar atmospheric features are during an eclipse, or if you can artificially occult the sun's disk, which happens in case of coronagraphs. So why do we need to study the sun? From school we have been taught that sun gives us life and energy, light and energy. But as we grew up, we came to know about some more things, that the sun emits, like there are solar storms, coronal mass ejections, high energy particles coming into the interplanetary medium from sun, and these cause the beautiful aurora that you see, but at the same time not everything is very happening and good about these. They can actually cause geomagnetic storms, communication disruption, radio signal disruption, space-based communication is disrupted severely. But the most important thing is that the sun is the most accessible and closest astrophysical laboratory that we have. So, if you study the sun, at least for stars which are of similar spectral category, which are of similar size as that of the sun, you can study nearly all branches of physics, including plasma physics, turbulence, electrodynamics, nuclear physics, everything on the from the sun. So that is the importance of why sun is looked into, even though it is more of humble in its origin and nature. So where does it start from? Where does all this energy come from? So it actually comes from nuclear fusion reaction. Again, nuclear fusion reaction in the interior of the in the core of the sun, in the interior, where about 10 to the power 45 high energy photons are produced every second, and each such photon takes about 100,000 years to travel from its interior to the surface. Thankfully, on Earth we don't have to wait that long. So whenever a photon, a visible light photon is there on the surface, it will take it just 8 minutes to reach us on the Earth. But apart from these photons which are created in the interior, in the core, there are another millions and millions of photons which are being created in other layers of the sun. So what are the other layers? So the other layers of the sun are actually the atmospheric layers of the sun. So the surface of the sun, when I was talking about the visible light photons coming up to the surface, this is how it looks like. So the surface of the sun will actually look like blobs of bubbles that are coming up from the interior. It is very similar to what you see in a pan of boiling water. So these are known as granules, and these are actually, if you see a Doppler velocity image of the same region, you are going to see that wherever energy is coming from behind, the hot plasma, the gaseous material that makes up the sun, that is the blue region, and these granules then give up their energy in the form of light and heat, and they cool down and go into the flow back into the interior in the form of wherever there is these intergranular regions where it is marked red. So this is known as the surface. Now we go on to the solar atmosphere. Now solar atmosphere is not as horizontally stratified as that of the Earth's atmosphere. In Earth's atmosphere, we know very distinctly where the tropopause is, where the stratopause is, where the ozonosphere is, everything. But for the sun, it is not like that. Just outside the surface, there is a layer which is known as a chromosphere, and the chromosphere is one of the most important layers of the solar atmosphere. Why? First, amongst all the layers of the solar atmosphere, this is one layer that can serve both as the source of heat and energy, as well as sink. For certain phenomenon, this same layer is going to serve as the heat source, and for some it will serve as the heat and mass sink, and that is simultaneous. It is not individual. So how does this particular layer balance that? How is that energy and mass budget maintained? So this is a critical layer, but then till now there have been only two space-based missions which have actually looked into the dynamics of plasma and energy in this layer. So that is where the solar ultraviolet imaging telescope is going to be important, because we are going to focus on the dynamic coupling of energy and mass in this particular layer. I'll talk about it in my later slides. After that, we have the transition region, which is a very thin layer, about 100 kilometers wide, and that layer is the most drastically changing layer of the solar atmosphere, where density, temperatures all shoot up. So this chromosphere, that is only about 20,000 Kelvin in temperature. By the time we reach the top edge of the transition region, the temperature will go up to 1 million Kelvin, and that is the temperature, the ambient temperature of the outermost layer of the solar atmosphere. So we have gone far away from the core where actual nuclear fusion is happening, yet then we are maintaining the solar corona, the sun is maintaining the solar corona, the outermost layer, at a temperature of 1 million Kelvin under every second, even now and always. So how does it manage to fuel that amount of energy into the atmosphere? So that is the corona, And the corona, the important thing about corona is that doesn't end. It doesn't have a distinct boundary where you say that the corona has ended. It diffuses into the interplanetary medium and just merges with the heliosphere. Now, I've already talked about those images where you see those dark spots. They are the sunspot regions where magnetic field lines are stronger, more dynamically evolving, complex topology. So, these are the magnetic field lines. Those actually give rise to that kind of sunspots. And these are the field lines that you see, the magenta colored lines. These are the field lines which have opened up, but they are not closed immediately within your field of view, but magnetic field lines have to close. So, they will close somewhere, they will spread maybe across the solar system, and somewhere they are going to close back on the sun. That is what that causes the geomagnetic storms. When such magnetic fields interfere with the Earth's magnetic field, that is when we have geomagnetic storms. Apart from these strong magnetic fields, don't think that the sun has only this much of magnetic field. That's not the story. It's the entire solar surface has magnetic fields. It's like a magnetic carpet, and the magnetic carpet is so, it itself changes so fast, like within a few minutes the entire configuration of the magnetic carpet will be changed. So, this is the region that if you see in the magnetic field region, if you see the photosphere, this is what it looks like. This is the sunspot. But as you go higher up, this same dark region will actually exhibit enhanced intensity. So, on the surface you were seeing that these magnetically active regions were actually holding back the hot plasma from traveling to the surface. That's why these are dark. But when you go to the chromosphere, you are going to see that it has enhanced intensity. And these same regions, since they are actually housing magnetic fields, when you go to the corona, you are going to see such loop-like structures. And these magnetic fields, since they are so dynamically changing, so rapidly evolving, many a times they undergo reconnection events which are associated with energy release events, and that is when you can see these X-ray emissions that are happening at those reconnection points. So, all these events are they actually need a lot of energy. At the same time, they are actually releasing a lot of energy. So, it's a lot of energy that is in the equation, and the entire energy budget of the star is very important for the entire solar system. Now, with the corona dissipating, like spreading out into the interplanetary medium, there is the solar wind that is flowing into the interplanetary medium, into the entire solar system. But at the same time, this is omnipresent. This is always there. This isn't a special condition. A special condition appears when there is an eruptive event like a flare or a solar storm, or even worse, a coronal mass ejection. A coronal mass ejection is when a plasma blob is detached from the sun itself, and it actually travels. Sometimes it travels towards the Earth, and sometimes it's directed to some other direction. But you can see from this image how large this blob of plasma is as compared to the size of the Earth. So, if you go by that size, and if this entire thing with its high energy particles, if it travels to the Earth, it is definitely going to cause some disruptions, some geomagnetic storms in the Earth's magnetic field. So, this is a flare. This is an image that is created by me during a part of my PhD. So, this is how a flare is evolving. You can see a sunspot here, a region of less emission, and this is how a flare evolves here. This is a ribbon flare. And this the intensity image, if you actually do an intensity plot of this, you are going to see that the intensity that changes by about a factor of 1000 as compared to the ambient. So, this was the data was taken from an interface region imaging spectrometer, which is IRIS. It is there in space, working till now in space, and with that data I had created this flare image. So, all this plasma along with the magnetic fields that are going into the interplanetary medium actually spread out in the interplanetary medium like a ballerina skirt. In addition to the magnetic fields spreading out, in addition to the plasma that is going out, we have to understand that the sun undergoes differential rotation. So, it is like a jelly ball which is twisted at different latitudes at different speeds. It's rotating at different speeds. So, what it creates is that these magnetic field lines also get twisted and they spread out along with the plasma frozen along those magnetic field lines. So, it gives the shape of this ballerina skirt. And this is where Aditya L1 mission is of importance, because Aditya L1 mission, which is going to be placed at this position, is going to look at all aspects of plasma and magnetic field that is coming out from the sun. In this image, you can see a blob of plasma spreading out, and then how it engulfs the Earth. And L1 point being here, the Aditya L1 spacecraft is supposed to understand all phenomena that are associated with the sun and the solar system. So it's a wholesome package. So if you go into this, this is the sun. As I told, the magnetic field lines are there. High energy particles are being channelized along these magnetic fields. And this is Earth. This is the L1 point where the satellite is going to be. This is the first dedicated solar mission by India, by ISRO. And it's a multi-institute, multi-research organization collaboration where many of the instruments are being built by these institutes. And of course, ISRO is the parent institute which is going to provide us with the launch vehicle and helping us with many of the technological aspects for these payloads. And once it is placed in orbit, it is going to take about 100 days for the cruise from here to there. And once it is launched properly, the initial calibration is done, then the nominal lifetime of this mission is about 5 years. So this is actually okay. So this is the audio is gone, I guess it's muted. So this is actually a simulation by ESA to show the LISA Pathfinder. The Pathfinder spelling is wrong, sorry. So it is the trajectory that this mission is going to take. A similar kind of trajectory is going to be taken by Aditya L1 spacecraft when it is launched from Earth and it reaches the L1 point, which is about 1.5 million kilometers from here. So it is far away from, sufficiently far away from the sun. So this is where it is going to trace out this halo orbit around that L1 point. Here you can see the spacecraft. It is these are the solar panels of the spacecraft which are not yet in a deployed condition. On the top deck we have the VLSC, which is a coronagraph which will create that artificial occultation of the solar disk. This is the suit. I don't know why the T is gone. It was there till now. Okay. And then there is this, there's one instrument which is known as a PAPA. There are two X-ray spectrometers, which is Solex and Helios here. Another particle instrument is here which is known as Aspects, and a magnetometer here, which is in the form of a boom. So whatever instruments are shown in purple, they are actually remote sensing instruments, and whatever are there in red, they are in situ instruments. So what is the difference? Remote sensing instruments means that the instruments are going to be housed on the spacecraft and it is going to look further away at the sun and do estimates, measurements, and try to monitor the sun. Whereas in situ instruments are going to sit there at the L1 point and going to try and estimate the plasma conditions, the magnetic field conditions at that particular location, which is outside the Earth's magnetic field. Hence, we will be able to understand the magnetic field of the sun and the interplanetary magnetic field conditions. So these are the in situ instruments. So basically, these are the So these are the instruments. This is the coronagraph. This is the ultraviolet imaging telescope that I have been working on. These are the two X-ray spectrometers. I don't know why this is scrambled now when I put it into full screen mode. And then the in situ instruments are PAPA and Aspects and the magnetometer. So the basic objectives are to understand the mass and energy coupling in different layers of the solar atmosphere, how it is spreading out in the corona, how these eruptive events are going to happen, to observe them from the very beginning till they actually spread out into the interplanetary medium in the form of coronal mass ejections, their effect on space and terrestrial climate and weather conditions, magnetic field measurements, particle acceleration mechanisms, etc. So all this, to do all this, this particular spacecraft is going to be placed in a halo orbit at this Sun-Earth Lagrangian 1 point. So this is just a summary of the slide of the objectives of these instruments. So I'll just skip it. So this is where it is. So this is what suit is going to do. The suit is going to observe the sun along this box. So that is about from disk center to about 1.2 solar radii. And the VLC imaging, which is mainly focused on the solar corona, that is going to take over from where suit stops. So it is going to look into the outer regions of the solar atmosphere. And this is L1 point, the Aditya L1 spacecraft. So it is going to monitor the particle conditions, the plasma conditions, and the magnetic fields using PAPA, Aspects, and magnetometer here. And it will look at the sun using Solex and Helios as the X-ray spectrometers, observing the sun as a star. And that is going to give us an estimate of when the flares are happening, because X-rays, the enhancement in X-ray emission is actually a trigger of flare events happening on the sun. Similarly, this VLC and suit are also going to sit here and look at the sun. So this is the instrument that I have been talking about. So this is the basic diagram of it. So this is the entrance aperture, the door where the solar rays are going to come in. This is the entrance baffle. This is the thermal filter or the entrance aperture filter, which is a very critical component for the success of this entire instrument. Not the spacecraft, but the instrument. So this has actually been a major part, the designing of it, fabrication and testing of it has been a major part of my work, because we had to ensure that this works properly. Then this is the primary baffle from where light is being guided towards the primary mirror, and then light flows into the secondary mirror, and then through the secondary baffle it passes through a vane shutter and is incident on a set of filter wheels. Filter wheels are basically like channels which allow light at certain wavelengths, and they will stop light beyond those pass bands. So a set of 11 science filters are housed on these filter wheels, and these actually help in passing light, which is coupled to which is going to tell us about some event, some phenomena that is happening on the sun. So there are 11 of those. So 11 of those are going to give you different informations. And then we have the focusing lens here, and then this is the CCD, the detector. And finally, there is this, you can't see it full here, this is the radiator heat pipe. So what happens is the CCD is actually operated at minus 55 degrees Celsius, but we do not have any active cooling mechanism for cooling that CCD to such temperature. So we will be actually using a heat radiator pipe, which is going to throw away all the heat to space and keep the detector cool. So as I said, those 11 filters are going to monitor certain phenomena and certain layers of the solar atmosphere. So what you are going to create is basically a height-wise map. Every layer, suppose this is the photosphere, then this is the upper photosphere, then these are different heights of the chromosphere, the intermediate layers of the solar atmosphere. And you are going to see how these features, how the plasma changes. Is it dark? Is it bright? What is the energy? Are there any waves in that? So that kind of intensity enhancements are there. So all those kind of things are going to be done by this instrument. So for this, what it is going to do, it is actually going to observe the sun between 200 to 400 nanometers, which is just outside the visible range. So that is near ultraviolet with a high contrast. So even for the ambient conditions, like it is not a flaring event, even then the brightest to the darkest features on the solar surface is going to have a contrast ratio of 10:1. That is how the instrument has been designed. And it is going to see as much as features as small as 1,000 kilometers in diameter. So if you can recollect the radius of the sun, a feature which is about 1,000 kilometers in diameter is pretty small, and it is important that you actually resolve it spatially. So we actually take images in all these 11 science filters, full disk like this, every 28 minutes, and then we will have highly specific regions of interest, which depending on the science objectives, like even you people can suggest some events which you want to see on the sun. So for that we do this kind of region of interest observations, and there the cadence is the temporal resolution is less than a minute, which is known as a cadence. So that is less than a minute, and this is a highly intelligent system. It is highly automated. So once it is taking its own full disk images and everything, suddenly it is going to detect the origin of flares or eruptive events based on the data that is coming to the two X-ray spectrometers that are there, and based on that it is going to do some onboard calculation and understand that yes, and it has to be again a confident understanding that yes, the flare has actually started, and that confidence level has to be reached, and all that thing is done on board. And then it starts tracking, because as I mentioned, the sun rotates at different latitudes with different speeds. This entire thing, this entire solar disk will keep moving, so the instrument has to keep tracking it and follow this event for next 2 to 3 hours, which is typically the lifetime of such eruptive events. And once they are over, this instrument is going to come back to its normal observation modes. Now also, like it is intelligent enough to actually have safety logic conditions. So on board we have certain set of onboard programming done, so that if there is a life threatening event for the instrument, it is actually going to shut itself down and wait for further human intervention from ground station so as to decide whether it is safe to start operating again or not. So this entire intelligence is built on board, and it is going to run on that with minimal human interference from ground. It will also have some automatic exposure controls, because I showed you that video where the intensity has enhanced by about 1000 times. So if you actually keep the exposure time that is true for normal observations, you are going to be completely blinded. You are just going to see a bright flash of light on the detector. So you have to take control of the exposure time, and once again the flare is over, it has to come back to its nominal exposure time. So all this is going to be done, and all this has been a part of my PhD work. So how did I join this project? As Dibendu mentioned, that it was a very humble beginning. This was the old SESI lab, and coming from the hustle bustle of Kolkata, I was very happy. Initially, I was very, very happy to see a field full of kash flower before Durga Puja. But it was, we were just 3 of us, and like students, we were 3 of us and few of the faculty members here. And we did spend some good time. The initial, regarding work, the initial planning of SUIT or Aditya L1 Mission, the seed money had all come. We had some initial idea, design specs that were to be followed, but everything needed to be, we needed to start working upon it, and that is where I started working. After joining here, after finishing my grad school, I actually was deputed to Ayuka, which is in Pune, and I conducted my entire PhD work there. This is a view of the SUIT board meeting at Ayuka. You can see all big shots with me, the only PhD student sitting there. So this was my work profile. I've already gone through it, so I'll just skip through it. So I had mentioned about this entrance aperture filter designing and fabrication, why it is so important. In a very broad overview that I'm going to give you, you can understand that the instrument is supposed to work here, and just beyond it we have the visible light. So if this light is allowed to come into the telescope, we hardly can see anything. Just like you can't see anything of the solar atmosphere under normal conditions with naked eye, you only see the disk. It is going to be something similar like that. So what we have to do is, this entrance aperture filter actually cuts down this light. Once you actually cut down this visible light, IR and everything, you realize that this is sun, and it is very, very close to us as compared to other stars. And the light that comes here itself within the operating wavelength of the telescope, that is going to create, like, even this light is sufficient to kill the detector. So what we have to do is, we have to create a kind of filter which can cut down light to some extent here, and then a major fraction of this light, and this instrument is supposed to work even when there is a flare happening. So this has to have a range, a dynamic range of such magnitude that under normal conditions it's going to cut off this, and under flaring conditions it has to cut 1000 times this light. So this is what the design of this thermal filter was important about. Once we did the designing, we actually tried fabricating it. Fabrication was another problem. We had to do it in collaboration with some vendors. And what we realized is that once we make the thermal filter, we have to be certain about certain things. There could be no pinholes on the surface of the thermal filter, because a pinhole is going to let all the light that we have been trying to cut out come. Even one pinhole is going to kill the entire objective of this. So whatever surface material, whatever surface coating we had to put, we had to ensure that that has no pinholes. Second thing, this is the first optical component that is going to face space. So it is going to be continuously bombarded by all the high radiation elements that are there at L1 point. So it has to be properly space qualified. Third thing is, whatever light is falling on this, we can't let that be absorbed by this itself. So a large fraction of this light, whatever is falling on the thermal filter, on the outer surface of the thermal filter or the entrance aperture filter, needs to be reflected back into space. So all these things had to be taken care of, and we had to make this instrument, we had to make this coating. The substrate of the entrance aperture filter was UV fused silica of a particular grade, and we had this multiple layers of chromium, aluminum and silicon dioxide to ensure that it doesn't undergo space degradation, as well as no pinholes are formed. Another thing that is important about this is vibration. So all optical components, space based, when they are launched, when they take off, they undergo massive vibrations and electrical shocks. So what we have to do is we have to mimic that condition here on Earth in labs and try to see that if that is going to break this instrument, that is going to shatter the particular optical component, is it going to kind of distort, is it going to bend this instrument, this optical component in some way, because all these are going to affect the image that you are seeing. So this is one of my colleagues, Mr. Ravi, who is performing this experiment to see. This is the vibration table that is there in URSC ISRO, and these tables are capable of generating vibrations of sinusoidal nature as well as random nature of given strengths that you want. And you are going to, I'm going to show you a video. This is the kind of, this is taken in a slow motion. So you can see how it vibrates. So since it is one of the low speed vibrations that I have shown here, because actually if you go for the high speed ones, you can't see anything, they are just completely blurred. So this is the kind of thing, and so tiny, so critical these components are that even this amount of vibration can actually break or create surface deformation. So we have to perform all those tests on ground, we have to simulate that condition and do it. Second thing I was involved in is designing the science filters. The science filters also had to be done in collaboration. So much of my work, in addition to academia, I had to work with vendors across the world for making these filters. So these science filters were made by Materion, which is a US based company, and we had to find out what are the typical thicknesses which can handle those, what are the coating layers which can give us the desired output, etc. Sometimes once these arrived, well, we had to check their actual emissions, transmissions, and sometimes we used to see that these filters, they don't have uniform transmission across the surface. So we had to see what kind of effective transmission these filters are capable of giving, because these filters, transmission of these filters is necessary. That is what is going to let light of a certain wavelength pass, and then only we can know what is happening on the sun at a particular layer or at a particular event. Also, the mounting of these are critical. So if you actually mount, there is a tilt of these. Sometimes what happens is, by our mistake or its lack of human precision, that there is some kind of tilt while we house these on these wheels, and that shifts the wavelength that we are looking at. So some of these science filters that will cater to our scientific objectives are as narrow as 1 angstrom. If the filter width is 1 angstrom and the filter, because of human error or whatever, if we shift by 1 nanometer, which is like 10 orders of magnitude as compared to the passband, we hardly capture that light. So we have to be very sure, and it is an iterative process. Multiple times we have to do it. Every time we have to undergo this kind of surface deformation tests and try to see that we are still looking at the wavelength that we want to. So once we have all the components, we undergo this process for every component that is there, both the mirrors, transmission filters, the focusing lens, everything. Once we have those, once we have the estimated, the measured profiles from these components, we try to find out what are the effective performance criteria. So there are figures of merit like signal to noise ratio, like throughput efficiency, all those kinds of things we need to see. So we are trying to see under ambient conditions features which will have a contrast of 10:1, which has that kind of emission the sun emits in UV, which is much less than that of the visible. And despite all that, we will have to make sure that within this exposure time limit, we can actually achieve the signal to noise ratio that we want. The exposure time of this particular instrument is actually governed by the shutter speed at which the images are taken, and also the drift of the entire spacecraft in space. So what we achieve is that the SNRs that we get is about 50 to 120 at the beginning of life in orbit. First time when it has started taking images in orbit, we are trying to get a SNR of about 50 to 120 per resolution element. But these transmission filters, as I have been mentioning, that they allow light of certain wavelength to pass. It is not that the transmission is fully cut off. It is not absolutely 0. It could be reduced by a factor of 10 to the power 5, 10 to the power -5 it becomes, but it is never 0. So there is a kind of light leaking into the imaging system at all points. So that light mitigation, that leak mitigation thing is still going on. We are trying to figure out methods, techniques where we could minimize these leaks so that the SNR is steadily above 100. It never goes to 50. So this is the imaging performance of the instrument. It is basically how, suppose there is a point source at an infinite distance, how do we see that? Our eyes see that, because we have with different eyesight problems, maybe our eyes are not same. So how do we, each of us, perceive of that point in a different way? So that is something equivalent to a point spread function for an instrument. So this is the point spread function image for the instrument. What you can see is that this is not symmetric across the CCD. At different locations on the CCD, it is variable. That is because it is primarily an off-axis system, so it is not symmetric. So at the center, if you have a point source at infinite distance, at the center you will have a perfectly circled PSF. But as you go closer to the edges, it is going to have some lobes, it is going to have some orientation, and slightly elongated in nature. As a result of which, the images that you are going to see of the same sun at different points on the CCD is going to be different. So if this is the original sun, this is the actual sun, then what you are going to see at the center is this, and what you are going to see at the edge is going to be something like this. So you can clearly see the difference in their performance. However, what we can see is that all the contrast points, all the brightness points, intensity enhancements, the contrast things, everything is captured in both in all conditions, under all conditions, even at the edge or the center. As a result of which, we conclude that this instrument is particularly of use. We are also talking about an imaging system. So in absence of any scattered light, this is the kind of image that we are supposed to get. So I had to do this extensive analysis using a non-sequential ray tracing, that all these optical components, optomechanical components, mounts, baffles, the paints that are used on the inside surface of these components, how do they lead to the performance of the instrument? So if you take into consideration all the scattered light that is there, the image that you get on the detector is not a circle, is not a disk like the sun. It is something asymmetric, and it is something like this, where you can see that there is a clear symmetry at the two edges. This is because, again, the system is an off-axis system. Now we are talking about a space-based instrument. It is going into space, and then we have no control. If it fails, it fails. So how do we know what to do? How do we know it is degrading with time? So to do that, we had planned, and we are incorporating a stellar calibration mode, where we are going into observing the modes of sufficiently bright stars within 200 to 400 nanometers. They have to be non-binary, and also they have to be relatively stable in this wavelength. And we have identified these two stars, Vega and Sirius A, which are light years away from us. And the instrument, once again, is going to go into this mode and observe and come back to its regular observation mode of the sun on an automated format. So this is just the space qualification test that every instrument has to go through. And we have I've spoken about the vibration test. We have the radiation test, where we talk about gamma radiation as well as proton radiation. We have different environmental tests, and all optical and electronic component that is there in the instrument has to undergo all these tests and pass with flying colors. Only then they are called space qualified. So this is me here working at the LINAC Pelletron facility, which is at BARC TIFR. This is a linear accelerator, where here I am putting a kind of this one of these electronic components or optical components, I don't remember exactly. And then we are going to bombard it with 21.5 mega electron volt particles, and going to see how its function, how it degrades because of that kind of emission. So this is one of those typical experiments. Let me tell you something. When I was doing this experiments, just before that, I had watched Chernobyl, which was this series that had come. And while I was doing this, I was always reminded of that kind of situation, though it is completely safe and it has got nothing to do with that order. So this kind of experiments we had to do. This is me working in the clean room, which is at SAG Space Astronomy Group at ISIDE Bangalore, ISRO. So this was my first day. I clearly remember I was wearing clean room suits, because this is a class 100 clean room, where dust particles of the order of larger than, I think, 0.5 microns has to be less than 100. So that kind of room this is, and I was wearing 2 layers of clean room jackets, and you can see pretty much all parts of my body except my specs were visible. So since it's an UV light imager, contamination is a major threat. So any kind of dust particle, any kind of lubricants, hydrocarbons, even your like our sweat is going to be a killer for these instruments. So we have to ensure that every component is clear, crystal clear. So what we do is all components, before they are mounted on this, we have to wear these gloves and everything because we don't want our fingerprints on sun when they come on the CCD. And we put this kind of polymer coating on the optical components and gradually peel it off. Now I can confess to you something, my rotis are never this gold, but my polymer coatings are always gold. So this was me, and we conduct it day in, day out for every optical component, and if this fails one time, we repeat this process until and unless we get the desired level of cleanliness. This was me working, this was me trying to assemble the DHA, which is the detector housing assembly, because before one of the vibration tests, so we had to, I was trying to torque it from beneath and then go for the vibration test, so as to ensure that none of the parts are broken, none of the parts fall off during the vibration test, because then it is rejected. So this is the kind of test that we do once every optical component that we place on this optical bench, which is the base platform for the telescope. We try to use an interferometer and see different kinds of figures of merit like astigmatism, power, focus, etc., and try to see whether that is of lambda by 4, or technically it should be lambda by 4, but we don't really get it. Actually it is ideally it should be lambda by 10, but we think that in practical conditions lambda by 4 is going to be fine. So every time one component is put, we do this, then we will put, suppose this is the primary mirror, then we put the secondary mirror and we repeat, and as a coupled system, as and when we keep introducing optical components, we have to make sure that the combined system's figure of merit never crosses lambda by 4. So that is the kind of, that is what is known as alignment and assembly. So that is the kind of work that has been going on, and this is the current state of the instrument. The entrance aperture filter is not yet there. This is the primary mirror baffle, this is the primary mirror, there's a secondary mirror here, and secondary mirror baffle. The focusing lens is in place. The detector housing assembly is in place. I don't think the FM level, FM quality detector is still mounted, but that will be the last phase. This is the front end electronics box that drives the detector.
Is that a heat pipe?
So I was coming to this. This was the heat pipe. So just like this base plate, this entire instrument is going to be covered on all sides by like a box, and this heat pipe is going to be on the top deck of it, radiating away all the heat into space and cooling, keeping the CCD cool to minus 55 degrees Celsius, at least minus 50. So since I was talking about the instrument being very smart and intelligent on its own, this is the kind of onboard processing that we have been planning about, and I have worked on this with one of my colleagues, Mr. Sakya Sinha, and we have incorporated them into FPGA modules, and it is already, testing is going on, and unless some safety logic conditions are required where like we need some human intervention from ground station, this entire thing is going to be done on board. Some joint observations, of course, we had to find out what our instrument can do, what other instruments can do, and if we can combine them. So this is the nutshell of my journey. So I started off with the Aditya L1 meeting in November 2013, which was 9 years back. So that was held at IIA Bangalore, and that was where I was introduced to my Ayuka bosses. Durgesh was there, and I think Dibyendu was also there, I don't remember, in 2013 meeting. So this was, of course, I tried to keep my working and my fun part separate, but I did have a lot of fun. So this was my first trekking done, then I saw my first snowfall, and I traveled quite a bit. Sometimes it's metaphorical, I traveled quite a bit for my PhD, in the sense that I was lost in what to do, work-wise. So it was like a non-ending path in a jungle. I don't have answers to questions that my bosses are asking. So that I did. Then I actually found some solace while walking along Mount Etna, which is an active volcano in Sicily. So I actually trekked on that volcano when the volcano was still spewing smoke. So all that fun was happening. I also traveled and went deeper, deeper, deeper. Like I went, I think, 60 feet below the ground to a Bronze Age copper mine, where people at that time used to dig out the ores with bones. So this is again metaphorical, dig, dig, dig. So, and finally, but yeah, I did try to keep my work separate from all this, from my travel. And finally, in 2019, 17th May, I defended my thesis. And that is when I come and I see that the group of 13 people, a group of 3 people, like 3 students, have grown into this. And now I see even a bigger group teaming with new teenagers and like younger people. And this is where I left SESI, and then I joined ISRO eyesight for my postdoctoral fellowship for a couple of years. And now I am working in TCS research as a scientist. So I'm trying to combine my knowledge, my understanding of how academia works, and some experience that I had while working with the vendors for building this instrument. And I'm trying to bring that into industry and take what is good in industry, take that experience back with me and pass on to my academia alumni people. So that is what my work is right now. I'm working on various aspects of Earth observations from space-based platforms, which could be of use to the human community. And at the same time, I'm coupling. So earlier, it used to be the convention used to be that academia is very separate. At least in India, academia is separate, industry is separate, which first, like in US and European countries, this started quite a bit ago, that they started merging, they started collaborating, and this is what now my work is. I'm collaborating between academia and industry as a scientist in TCS. Yeah, so thank you for your patience. That was my journey during my PhD as one of the students working on a space mission. Thank you.
Do you have any questions for her?
Actually, I do have.
Sure, go ahead.
So it's a bit of a trivial question, but how does the sun actually have the magnetic field? If we study Curie's law, then at higher temperature, it should get destroyed, right? Yeah, so that's a very basic question, but I'm still lost.
I can answer that question, no problem. It's just
Yeah.
completely besides the talk here.
Yeah, so
Yeah,
Dibend is a better person to answer to
Yeah.
that question.
Yeah.
So anything else related to my, I knew it. So Varun has been my colleague even at Ayuka for 6 years. So we have a long association. Yes, go ahead with your question.
2 questions.
Okay.
One is, how does Aditya compare to Parker and other current solar missions? And the second question is, if these students want to get involved, right, would you recommend they should, and how should they go about it? Not just Aditya, but in
general.
In general.
I'll talk about the second question first. So if students want to get into this kind of challenging projects in their PhD, it is a welcome, but I'll give you a fair warning that it is a challenging task. But you are always welcome. There's always an end to it and you will succeed. But so if you want to get into this, SESI is a good platform, like I started from there. There are several other research organizations right now, even industry, like where I come from, they are taking in students from different IITs and everything. And they are trying to place these people in such ambitious projects. So you can go, you can register for these kind of things, you can drop in your CV, and once you are selected, you can go for an internship in the beginning, like while doing your masters and everything. And once you choose what you want to do about, then you can register for your PhD at different, this kind of like JAP was there earlier. I think JAP is still there. In IISc Bangalore, you can register here. Like SESI provided me a very good opportunity in terms of working with Ayuka, IIA, ISRO, everybody. So it is possible to do. You just need to find out what kind of projects are going on, what are the upcoming projects, like Daksha is there. And you need to drop in your CV and you need to contact those people and show and tell them how you can contribute. I am not saying that you can right now, being master students or bachelor students, you can exactly pinpoint how you can contribute, but you can at least say what you want to do clearly. So that from there you can actually, these people are experienced enough to know where your niche is, where you could be put, where your contribution could be significant. Does that answer the question? Okay. So the first question was what? Sorry.
How does Aditya compare to existing solar missions?
Okay. So existing solar missions, Parker is a very different category mission because it is going very close into the sun, and in due course of time it is going to crash into it, right? On the other hand, this mission is going to stay there at L1 point observing 24/7 for the nominal lifetime is 5 years, but if you go by the track record of missions of NASA, they are actually, some of those instruments have worked for 20 years. So this is going to sit there, and since it's at the L1 point, it is never going to go beyond the Earth. So it is always going to, it's going to do 24/7 observations from that point. And all the other instruments that we have, actually SOHO was one instrument which was at the L1 point. Most of the other instruments are Earth orbiting instruments. So at some point in time, they actually go beyond the Earth. So that is a shadow period, and we don't have data for the sun. So this is where Aditya mission is going to be of importance. And some of these instruments are actually going to look into layers which have been layers of the solar atmosphere, which have been kind of ignored till now. Not exactly ignored, but there were lesser number of observations for those regions. But they are very critical. So that is where Aditya L1 mission, and particularly the SUIT instrument, is going to be of use.
Was the timeline of the Aditya L1 mission planned in a way that sun's solar cycle is like rising up right now?
Yes, it was. Yes, as far as I know, I mean, when I joined, this planning was all done. Dibyendu was one of those members. But as far as I understand, it was dedicated to a rising phase of the solar cycle. But you know, things don't go as we plan. So we have missed it, but we are hoping that we are going to get the next cycle. So we will do it. Maybe we will capture the decaying phase of that solar cycle and then the next rising phase. So you know, it's 11 years, so 5.5. So we have gotten delayed by 3-4 years already. I think so. Initially, the launch was planned around 1920, but then Corona happened, so everything came to a standstill. By 23, we are already going to be 3 years beyond schedule. So then we are going to get the lagging phase and then the next rising phase.
My question was regarding the kind of science that we are doing that is completely of exploratory nature. So how can industry find some way to make revenue out of this? Like how can
because industry knows how to encash on science. So whatever you know, whatever we do as exploratory science, they know how to convert it into industry. Like they use technologies. Like if you start an experiment, like if you go by J.C. Bose's experiment, the first microwave experiments that he was doing, that was an experiment. But now companies have started using those microwave technologies, right? So industry will find a way how to use that to human benefit and to the benefit of revenue. So that is their part of job. So they are actually into exploring new projects. So what they are trying to do as businessmen also, they are trying to expand their horizon of science so that in due course of time that science can be converted into technology. What is today's science is tomorrow's technology. That is one of the logos that I have read at TCS actually. So that is what their principle is. So if they support science today, they will find a way how to convert that to technology tomorrow.
Could you give an example of how like solar physics, like, at least from your viewpoint, how you see this becoming a technology in the future? Like, will there be any sort of a
no, it's not going to be. No, solar physics as such is not going to do. But whatever technology we are developing for observing solar physics, it could definitely be applied to human benefit, right? All the technologies, the imaging technologies that we are trying to do, the kind of sensitivity we are trying to develop for these instruments, the kind of sensitivity Varun was trying to talk about. Of course, we won't be needing that in human lives, but we can always strive to get something better. So solar physics, actually solar physics will have some role to play for us also, because some of these emissions on the sun in this particular wavelength band in neo ultraviolet actually has a direct role to play in our terrestrial climate weather, right? The ozone dissociation and oxygen formation layer. So whatever is happening on the sun that is going to tell you what is going to happen in our ozonosphere, right? So if you develop something which is technologically more advanced, you can do that estimate better. You can actually say what is going to happen to our ozonosphere in a better way. So that is going to benefit the human society. That is going to benefit, like, companies which are going to get into this kind of work, they are going to earn revenue by helping the government's project that ozonosphere is depleting, ozonosphere is replenishing, right? So that kind of work is always there. Yes.
Why the L1 point? Why no other point? What is so special about it?
Because this is, the straight answer is because it is along the straight line between sun and earth, right? So if you go to some other point which is beyond the earth, like James Webb has gone, there is no point, right? And going to the L2 and L3 points, like the other points, no, they are called L4 and L5. So those points, they are actually, they are of no use, because if you want to use that points to your advantage, you have to have stereoscopic view, because you are going to be placed at one side. So you're going to see sun from here only. So if you want to have that advantage, then you should have a stereoscopic. You should have a couple of instruments pointed at, located at those two positions, and have a stereoscopic view of the sun. That is a very good idea, but it is a very ambitious project. So depending on that, this L1 point is a comparatively easier achievable point in terms of trajectory, and also in terms of direct view. Telemetry, yes, telemetry. Because this is in a straight line. So you can always keep sending in signals, you can receive signals in an easier way.
My question is that, how has your experience been in transitioning from academia to industry?
It has been fantastic.
Okay.
It has been very good.
Okay. I mean, like working at TCS,
No, it is actually, maybe because I'm still at TCS Research. So my transition has been extremely smooth, and touch wood, it's good. And I have no regrets.
We'll take one last question and then we'll close.
Hello. I have one question that what if the spacecraft, Aditya spacecraft, misses the L1 point? So is it like, it may happen, I don't know. I don't know much about orbital mechanics. So if it misses, like it becomes like a Parker solar probe and it keeps on moving towards the sun.
There is a high chance, like there is a...
Yeah, always this.
It is not improbable. There is some probability that we are going to miss it. And that's a luck thing, okay? I mean, there's a very tiny probability, I think.
And if that happens...
And if that happens, either it is going to come into the Earth's gravitational field of influence, or to the sun.
will it still be taking the measurements?
Sorry?
Will it still be taking the measurements?
No. Because in the cruise phase, there is no observations that are going to happen, unlike Parker Solar Probe. So it will go to L1 point, then it will be having, which it will take around 3 months to go, and then it will be having some initial calibration phase, and only after that all instruments are going to be they will start operating only after all those phases are over.
Okay, thanks.
So one small thing here is L1 point is a L1 region really.
Yeah, it's not actually one dot. So it's a halo orbit, it's a kind of region around it.
Okay, thank you, Avyarthana. So I think what I'll do is I'll take a question, which is an interesting question, cool temperature question. So the sun is not a solid body, it's not a magnetic material. So cool temperature is really, related to magnetic materials who have aligned dipoles, and you raise the temperature beyond a certain point, and you get in disorder, so the large scale magnetism is lost, right? In the sun, the magnetic field is produced through a mechanism which is known as magneto-hydrodynamic dynamo action. I'm not going to go into the technical details of that, but in a nutshell, it is a mechanism which converts the energy in plasma flows into magnetic energy, in a very simplistic term. So the mechanism of production of magnetic fields is very different, unlike what you see in ferromagnetic materials and all that. One question was asked about this is by Varun, why is the Aditya mission, how is it different from other solar missions? Two very important points are that the Aditya mission has a coronal magnetometry feature, which is measuring the magnetic fields of the sun's corona from space, which is highly challenging. If Aditya can do this, it is the only mission in space which would be doing it. Number two, the instrument that Avyarthana herself has contributed to. The wavelength range, 200 to 400 nanometers, is particularly significant for climate dynamics. There is no space-based telescope which is observing the sun across this wide range of near ultraviolet right now. So those are two very, very unique characteristics of the Aditya mission. So Avyarthana, thank you very much, as well as Varun, for coming in, taking your time off and traveling all the way to Mohanpur to be with our students today. They are going to be in Science City. I think Varun is leaving tomorrow evening because he has to do many other things in IUCA and IIT Bombay. Avyarthana is going to be with us over the week. She's going to be part of the Women in Space Science panel. Those of you who are interested in industries, please come to our Industry Academia panel on Sunday at Science City Mini Auditorium. You're welcome to come and visit us and explore what the discussions are going on, what the opportunities are, and there'll be various people from both the industry side as well as the academia side in the Industry Academia panel. So once again, remember that you're all welcome to Science City. You don't need anything from here. You can just go contact the help desk that we have right in front of the entry gate, and from there you can collect the passes for the partner organizations and get in. If you have any issues, just contact us. Thank you very much, and with that we close today. Can I have a photograph with both of you with all the students in the background? So you can all come in.